Welcome to qnawire.
In this problem, let's see here, we're going to go back and look at problem 37 and look at the exergy destruction. So again, we can get the entropy at the pump side of things, at the pump, because we know we're going to assume it's a saturated liquid at 10 kilopascal. So we get the entropy on the inlet and the exit of the pump. And this would be actually, this should be a prime here because in this case we didn't have a perfectly efficient pump or an isentropic pump. And then we can go back and get the entropy at the various points in the process that we calculated before. Again, some of these I think we got, let me see, problem 37. Some of these I think we got from, we can get from the, because we know there were some efficiencies in the turbine and things. So we have to look at the, once we got the entropy in the inlet, and then we assumed that the entropy at the outlet was the same as the entropy at the inlet, and then we got the isentropic efficiency, isentropic enthalpy, and then we found the real enthalpy. So then we need to go back and find the real entropy, which I've done here, but for like some of the exit states coming out of the different devices. So again, that's all simple enough that I think you can do that by now. So again, we have two two thermodynamic properties at every state, so we can find whatever else we need. Now I also grabbed the enthalpy at 3 because because they asked for just uh, the exergy of the steam at the boiler exit. So we needed that. Okay, so let's see here. Is there anything else they told us in this problem? Oh, P naught. Yeah, P naught is the usual 100 kilopascals. And then we have the high and low temperature heat transfer to the boiler into the boiler comes from 1500 or 1600 Kelvin source, and then the heat transfer to the from out of the condenser goes to a 285 Kelvin source. So now we can basically there's various ways of going about this problem. I'm going to basically look at this is the exergy destroyed. If you look at both the what do you call it, the pump and the especially with the pumping process. All right. Oh no, sorry. This is the pumping process and the heat addition. So if you basically go put a control volume around the pump and the heating, uh, let's see. Actually, let's go back to problem 37. Let's go check a look at that. Let's see if we can find here. Problem 37. Here we go. So problem 37. Right. So we have. I didn't draw a diagram of it, but we have the pump and the heating. So from here to here and then here to here, we have heating. So again, these were not isentropic, so we have some losses there. So okay, let's so we have basically we're looking at the pump um, combined the from here to here. We look from that. We change the change and there to there, and then also from there to there. So that's the pump plus the boiler, and then the reheat from the uh, turbine out bleed. So then let's go back to our last problem here. Let's see here, what problem are we doing? I can't remember now. 62. 62 is here. All right. So this is the change in exergy destroyed, and I called it total, but it's not like the total. It's the total for the boiler and the pump. And so here's the change in entropy going into the coming out of the boiler and then going into the pump. And then this is the change in entropy of the stuff that's coming from being reheated. And then we have the heat transfer entropy from that. So from the heat transfer going in to the boiler, and then divided by the temperature source. And plugging all this stuff in, we get 2,000 or 1,290 kilojoules per kilogram. Now we can estimate the exergy of the that's destroyed in the pump, because again, remember, it's not perfectly efficient. So this would be the isentropic work, and this would be the actual work. And so we found what the actual work was. The isentropic work would be, just the specific volume in the pump, the water in the pump times the change in pressure. And so we can get all of it. We have this, and in fact, we essentially calculated that, but then divided by the efficiency to get this. And so in the end, we get the exergy destruction in the pump is very small. It's 0.53 kilojoules per kilogram, and it's especially very small compared to that. So the exergy destroyed in the heating process is, let's see here, is this minus this. And so that winds up being 1,289 kilojoules per kilogram. And basically what we did is we avoided finding S2. We had S2 prime, but got around calculating S2 by doing this process here. Not sure if it was worth it or not, but that's what I did. And so then we look at this is the exergy destroyed in the turbine, which is adiabatic, so that's gone, but is not isentropic. And so again, the different stages of the turbine, and we have all these entropies. And so we can plug everything in, and we get about 248 kilojoules per kilogram. So not a whole lot of exergy destruction there. But again, we're assuming that it's adiabatic. And then they wanted the exergy at this and steam of the steam at the boiler exit. So this would be kind of the theoretical work that we could get out of the steam at the exit. So then that's the enthalpy at the enthalpy at the exit of the boiler minus the enthalpy at the reference conditions, which is I looked up here, and then here is for the entropy at the exit. So minus the surrounding temperature times the change in entropy from the exit of the boiler to the surroundings. And that winds up being very close to 1,500 kilojoules per kilogram of theoretical work that we could get out of the steam that is coming out of the boiler.